stuff. So we'll start with how we transformed something complicated in something easy. So I'm not sure, I suppose that a lot of people who are here are interested in remote sensing, that's why we are here. So basically I will give just a super fast introduction to hyperspectral imagery, and then we are going to show you what we did. So basically why we did this in hyperspectral. So hyperspectral imagery has a wealth of information. So if you imagine multispectral imagery like Sentinel-2 and Landsat, they have 10, 12 bands. Each band is like represents a number of the wavelength reflectance on some portion of the spectra. Generally, like multispectral have between 30 and 180 of spectral resolution. Well, hyperspectral have like 2, 5, 6 nanometers. So if you imagine Landsat and Sentinel have one red, hyperspectral is like doing Carpaccio from it, having a lot of reds. And each portion in the wavelength spectrum tells you something about its like properties, chemical, geophysical, ecological, like there is really a lot of applications. So generally, here you can see a hypercube, which is a really cool way to represent hyperspectral data. So the borders just represent all the variation of the spectra on the borders of this cube. So generally, like hyperspectral data is something that scientists work from the 70s, basically, but it's so heavy in means of data dimensionally, like, and also so heavy to do because of that complex analysis that was not really a great thing until a few years ago, something similar like machine learning actually. So basically this is the future of remote sensing. So now there is a lot of available missions like EnMAP, PRISMA and Tanager. Before that there was also some of them like the cool Hyperion from NASA, which was like 20 years I think in orbit, throwing out hyperspectral imagery with 30 meters resolution, but it was more to prove a concept than to use it. So there is many upcoming ones, so I'm looking really forward to CHIME and FLEX, which will be for ESA, so free data. One will be focused in generally hyperspectral imagery, one more about portions that are representing fluorescence for plants. So, but there is also other, Hyperlight and YAM, yet another mission. So we are talking also about commercial satellites that will offer the data. So there is also something that is going to shift from multispectral to superspectral. So if hyperspectral it has 400 and something bands, superspectral, let's say, has 50, 60, 20, depends how you define it. So one of the missions that is going to be superspectral is the next Landsat, which is called Landsat Next. And in the moment when we get an amount of data that is so near and so rich, we have to start to do some preprocessing in a different way that we do with multispectral. So yeah, today we can do that really easily, digest them and do crazy machine learning with them. So the main thing is that people are focused on what they want, and they don't want to be really data engineers for every task. I don't know, you want to classify some minerals, not have a PhD about how to cluster and send the process to a computer and to calculate it. So this is why we're motivated to do a simple add-on that lets you do all the preprocessing steps in GRASS. So why GRASS? Like its speed, its efficiency, and it's connected directly to a lot of state-of-the-art algorithms. So people love to use Python for general 3D matrices analysis, which is great, but there are some tools that are better for spatial data. So if you are doing some spatial interpolations, for example, you can find really state-of-the-art algorithms in GRASS. So it's pointless to use it from SciPy and stuff like that because they are focused on a broader range of signal analysis and stuff like that. So rasters are managed in GRASS like, I would say like a database. So you can have big rasters, then focused on parts, which are practically something like index in the back. So you can just have large data, jump to a specific defined region, calculate it there, and go elsewhere. So what is really great with GRASS that it's in the harmony with the whole Python ecosystem. So you can use GRASS from command line, you can use it from Python, from R, and so on. What I really like to do as somebody that loves to have as much as possible tools right now is to work with GRASS as a data storage for rasters, and then if I come to a part when I want to use state-of-the-art machine learning algorithms that are from PyTorch, I can call all the 3D array with just this function. So it just calls, ingests all the raster, in this case a 3D raster map from GRASS, directly into NumPy. You do whatever you want, and you throw it back like a baby, and it's spatially there where it's supposed to be. You don't have to fight with the metadata and so on, because GRASS handles this. So the other thing is, I think that GRASS is really good for doing add-ons that are academically, scientifically oriented. It has a really well-maintained add-on ecosystem. Like the documentation generally is very rich because it has to be, and it has a really big and lovely community, and everything is standardized. So here is like the main gaps which motivated us to do that. So I said already before, it's highly dimensional data, and there is many preprocessing steps that are classical. So you get a really noisy hyperspectral band, you have to smooth it, you want to search differences with different algorithms, blah, blah, blah. And you can do that step by step or have a pipeline that does it, for example. That would be really cool. So there is high data collinearity. So we imagined it's like a wave, a spectrum. So there is a necessity to have also algorithms that do some dimensional reduction that makes it then easier for your computer and for your models to find meaningful things here. So the visualization of preprocessed spectra is a good thing. So you see if you threw out your data from micro nanometers and gaps, or you just polished it. And then there is really a lot of non-standard imagery formats, which is really annoying, like one satellite in H5, one geotiffs, one that. So come on, let's import it in the same way, have same metadata, and then work on it. So this is the main gaps that we solved. So we did a harmonized import, which outputs a standard 3D raster. So this is the terminology that GRASS uses, so I must use it. And it has consistent metadata. So in the metadata, it stored the wavelength of each band, and then the spectral resolution, the validity. So some hyperspectral data are preprocessed, for example, with some atmospheric corrections, and some bands get the tag invalid. We can keep them and just tag them as valid or invalid, and then let the user do with them whatever it wants. And then the unit. This is also a thing. A lot of data has unit wavelengths, nanometers, or when we are talking about radians, it's unitless. So we solve this by that we created an importer that knows what are you importing and then sets it up. And then after that, it also plots it. So it's scalable. So scalable, it means that we optimized how some workflows work and how some dimensionality reduction algorithms are processed. And then there we built also spectral visualization module that also allows you to export this spectra. So once we're inside GRASS, you can do whatever you want. As I said before, you can then preprocess your data in other various ways, interpolate it like different types, then in the end have your data prepared for doing crazy analysis. So what we did here, we did a multimodal add-on that is intended to be used step by step in a workflow logic. So there is i.hyper import, which imports. Then there is the i.hyper composite, which lets you check what's being imported in means of creating 2D false composites. Then the main thing here is the i.hyper prepros, which is for preprocessing. Then the explore for checking the spectra that you prepared, and then the export to export it from GRASS and use it elsewhere. So i.hyper import for now imports PRISMA, EnMAP and Tanager satellites. Until now, I think that this is the first open source tool that also imports Tanager data from Planet, which I think they sell it georeference, but we do the georeferencing here for you. And then this importer creates the hyperspectral 3D raster maps. And then you can choose also during the importing if you want the module to create some classical false color composite. So we let the user to choose if it's RGB, like color infrared, like, and then other, I would say, standardized visualizations that are good for like agriculture, geology, or just custom, because like every satellite has its own wavelengths, different matrix, but generally it's the same scale. So it is really stupid to go to search what bands do I need from Sentinel-2 and Landsat-2 show this. No, you have to define the wavelengths in nanometers, and then this importer checks where is the nearest band for that nanometer portion and create it for you. If you are not happy with what you've done, you can use then i.hyper composite to redo it from already imported data. So all the data here, when it gets imported, it gets the standard metadata, and this metadata is like a base for further preprocessing. So this is an example of how to import data from PRISMA. So as said, we have H5 data like EnMAP from Germany. They have like a multi-file, which is super boring. We solve this as making the importer that you have just to point or to a data or to a folder, and then the importer already knows what you want. You have to just to set which satellite is. So this is an example of a line of code. So PRISMA, which is an H5, input output, and we created the sphere for geology, and this is how it looks. The 2D composite. We have not photos here of the 3D cubes, but I will show later how the metadata looks. So this is another example of how to do the import for EnMAP. You just go to the EnMAP folder, do the same, pick another composite, bam, it's created. And below you can see also how can you set your own composites. So for example, this one is really good for ice. I don't know that there is no ice. This is from Netherlands, really now here. But you know, if you are searching for some clues in your data from Antarctica, it's pointless to do it with near infrared. But you have to choose different visualization techniques. So this is how it looks once in the classical GRASS GUI, but you of course can do it from the client, from the Python, and so on. This is the metadata in the right block. When you see that every band has its own designated wavelength, and the spectral resolution in this means like that each central wavelength captures 7 nanometers. So that if you divide it by 2, it means that between every band there is 3.5 nanometer. So this is generally then how it looks. Here you can see the EnMAP that was imported. This is the 3D. So if you go to the 3D raster model of GRASS, you can also color it and do hypercube like I showed on the beginning of the presentation. So composite, as I said, it does the same, so we should not discuss too much about it. You imported it, and then you saw that you did the RGB composite and you want one for agriculture. Okay, just do it here. So the prepros gives you the general preprocessing steps, operates on 3D hyperspectral raster maps. And what is really interesting here, which is not which is not the classical GRASS philosophy, it defines a pipeline. So if you want to do more preprocessing steps, you can just click them, and the module for preprocessing knows which order they should be done. And in the end, when you run it, it also shows you. I will show you later. So one example is like the Savitsky-Golay filter, which is a high-pass filter used also for time series, but here is really important because there is high frequency noise. So you use it. This is the first step that you do always. So this is why also we introduced it here. So then you can choose here, like if you want a classical Savitsky-Golay or do derivatives. So I will show pictures that's going to be easier to understand what is the polynomial smooth that you want to do, and so on. So there is many parameters that you just define. So for example, this is in blue there is a noisy original spectra, and this is the result from the smoothed spectra. So just imagine if you want to search some local variations in your data to find, I don't know, organic carbon. If you don't do this, you have a lot of false local minimums and maximums, and you are stuck with analysis. So this is the first step. So this is how it looks also from the GUI. You open it, you just set polynomial order. The documentation in the end, it's really nice. And of course, if you want to run it after that in the CLI, you just can copy the data. Here is all the GRASS lines. So imagine this line does Savitsky-Golay. If you're going to check classical Python workflows which do that. It's at least not a huge block, but it's let's be clear, it's a bigger pain in the ass, especially if you want to do it pixel-wise. So then there is a baseline correction, which removes like some strands, corrects offsets, and so on. And if you want to use it directly with Savitsky Golai, you can check one, check the second, then the algorithm first preprocesses with smoothings, then corrects the baseline. This is generally a shift that is done like that. It is accounting for some sensor differences. So another one is the continuum removal, which also accounts shifts that are connected with angles. So that one was just like this. This is also like that. So remove spectra via convex hull normalization, which basically means that your original spectra is like this. Then it calculates a convex hull and subtract it. And this is then the result, which is way better to search some slight things. Similar things are also for the first and second and third derivatives with Savitsky Golai. So this is an example of pipeline example. So for example, we want to, this is not a pipeline example, this is just dimensionality reduction with wrong title. So we want to manage high dimensionality, reduce collinearity. So generally people love to use PCA, which is great, but not all data has a linear relationship. So there is other types of dimensionality reduction which are used for that. One of them is kernel PCA, KPCA, which is super heavy, but we set the option for the user to use the parameters to do it chunk-wise. And there is another one that is the Nystrom, which I highlighted it, which does a kernel approximation and then transform it furtherly with PCA. Anyway, it is able to retrieve non-linear dimensionally reduced components from your data, which is good because not everything is linear. So we are offering linear and non-linear options here, and the chunked processing. So if your computer is really slow, you can say 10 chunks. It means that it will use 10 pixels per 10 pixel and then in one moment finish. So what is really important when doing dimensionality reduction is that after that you want to do some machine learning probably. So you maybe have some laboratory data that you want to use to change your data. If you want to do that, you have to transform your laboratory data in the same way this was transformed. Because if you do two separate dimensionality reductions, they are done based on how your original data is, so they are not comparable. That's why there is an option to export these fitted models in a pickle file, and in documentation we have also the example how to then apply this to your spectra from laboratory, which is imported in Python in a text file. So, and this is what I missed from the original PCA from GRASS, which Marcus made, which is really great and fast. But I think that if you want to use it generally, you have to have also a model for retransforming other data in the same way. Okay, this is the pipeline thing. So, okay, let's throw everything. Do Savitsky Golai, interpolate missing values, invalid bands, because there is options, and so on. Preprocess it in chunks, and then export. This is how it's done. So it is a big code, it's a big process. So in the output, in the end, the console outputs you also what you are doing, so you are sure what's happening. So Savitsky Golai, then baseline correction, then continuum removal, like this. So generally, then we have also the model that lets you explore this spectra and check it out and export it in different formats. So it looks like this. You just go around, click on the preprocessed, and you compare spectra, and you can export it, put it in your articles, and so on. So generally, this is how it looks also for radians. As said before, we'll check the metadata automatically. This is reflectance that was read by our metadata, and if we perform it on a Tanager, which is disseminated in radians, we get directly from the metadata the unit, so the user cannot fail. So generally, the export model is to export all this data. For now, it's just GeoTIFF. We are quite confused about H5 standards because they are not still there, but we want to implement more of them. So generally, like i.hyper offers you these all preprocessing steps, and once inside your GRASS, you can really work within GRASS, go out and have more from your data. So there is a lot of future work that we want to do. So we want to make importers for different satellites, like from legacy Hyperion, for high seas, Indian satellites, and so on. Store smarter metadata in a smarter way, possibly something related with JSON, and then do more export formats and standardize them. So, and not just pure data, but also metadata exports. So we want to do an aerial imagery module. Sometimes you have two cameras, just visible infrared and shortwave. You have to put them together. We know how to do that, but we did not have time to do that. So atmospheric correction, field spectroscopy, blah, 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 blah. So this to-do list is going to finish on GitHub in a proto roadmap. So basically, this is it. If you have any questions, ask now or write. Thanks.
Any questions in the room?
Yeah, thank you. Great talk. Yeah, I've never worked with like hyperspectral imagery. What would you say are some of the best like open data sources to start getting into all of that?
So are you interested in having some scientific proofs or to have some repetitive tasks? So for repetitive tasks, you have to buy generally now. Unfortunately, you have to buy data in Major Leads Planet. But for science, like EnMAP and PRISMA, it's free data, but you have to apply it for it. So you can, when applying, you just have to say what you're going to do, choose the region, and you can also task satellites. For example, I don't know, you are searching for, I don't know, nitrogen content of some different crop type that is bare soil in April, and then you task it from April to June with this and this preprocessing module, blah, 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 and
okay, yeah, that's actually exactly what I'd be interested in.
I can show you later.
Okay, cool.
And if you need some data, I can give you. There is a copyright clause, but they will not know. But they cannot prove it.
And if I'm not wrong, also for PRISMA, you can ask for research.
Yes. For PRISMA and for EnMAP, it's quite straightforward.
Yeah, so you can ask and they give you
ask
without any problem.
Ask and task. So, but you can have already a database you can choose from, but you also can just tell them, I want that piece of the ocean, and yeah.
Yeah, I think mine is an extension to what these guys have been saying. But when you say this is available globally, how global is this? Like
the data or the toolset that we... this is another topic.
Yeah, but the data.
I think that for tasking, it's not really a problem. You can task basically whenever maybe there are some political or similar constraints, I'm not sure. But if you go to PRISMA or to ASI, I want to task it whenever, Antarctica or Chile or whatever you want, no problem. Yeah.
Time for one more question.
Yeah, not really a question, just this is, well, I'll definitely be looking into this. I haven't actually worked with GRASS at all, so I'm going to be downloading that and having a look. But the company I work for, we do a lot of mineral classification and identification, so we've developed an in-house Python library to manage hyperspectral imagery. So we'll definitely be looking into this and seeing where there's overlap and comparing. And
it would be really good that if you have some comparison, you write us something. So yeah, but you're probably also doing the same pre-processing stamp and everything.
Yeah, we've got a lot more lines of code than I imagine we need in
That's great, we're better. Thank you.
So, no, great. So, thanks, I'll be in touch.
All right, thank you very much, Alan and Thomas, for coming out and presenting your work.
Thank you for the questions.